You are given an array of unique numbers that originally covered every value in some range, but a few numbers in the middle got removed, though the smallest and largest values are still there. Your job is to figure out and list, in order, exactly which numbers are missing from that range. If nothing's missing, just return an empty list. Advanced level, unique integers, originally a contiguous range from min to max, now with some integer values dropped. Recover the missing ones, sorted. Standard setup for an implicit range problem. This is the same shape as gap detection over any dense key space. Missing auto-increment IDs, drop sequence numbers, holes in a bitmap. The generalizable insight is turning a membership question into a positional one. Num6 1004 I 2005 range is 1.53 is absent. Trivial by inspection. The interesting part is doing it without a hash set. The whole solution rests on one observation. Since the values form a contiguous range, there's a bijection between value and array index num maps to num low. That means you can encode scene as a property of the array itself rather than in a separate structure. Sign bit as visited flag, abs to make the flip idempotent so a duplicate touch never unmarks it. Baseline for each value in range, membership test against nums. ON list membership makes this ON naively or ON time with ON extra space if you build a set first. The tracker version matches that time bound while cutting the auxiliary structure to the output array itself. Tracker I below plus I initially, so position encodes value with zero collision risk. It's a perfect hash by construction, not a heuristic one. No probing, no bucket chains, no hash function at all. Mark pass, then sweep pass, both ON, no extra space beyond the tracker, which is really the output buffer wearing a disguise. This is the same reuse, the input as class phrase family as the classic find all duplicates in an array trick. Each value routes directly to its slot via num, low, no search. Index 2 stays untouched. That's the eventual output, forming implicitly as a side effect of the marking pass. Positive survivors are exactly the values, with no corresponding entry in nums. The sign bit is doing double duty as both a visited flag and a value carrier, which is what lets one array replace two structures. Abs before negating is a detail that matters. Without it, a duplicate value would toggle the sign back to positive and silently produce a false negative. Since the problem guarantees uniqueness, this can't actually trigger here. But it's cheap insurance and worth knowing why it's there. Sortedness is free here because tracker was constructed in increasing order and filtering preserves order. No comparison based sort, no extra ON login. Full function, unchanged from the pieces above. Numlow is just a change of basis, shifting the range so it starts at 0. It's the same normalization you'd do before any array indexed encoding of a bounded domain. Learn 1 high 5, tracker 1000, 2000, 1005, 5. Marking 5 and 1 leaves indices 1000, 1003 positive, 5, 2000, 30,000, 3003. Nothing new here beyond confirming the invariant holds with a sparser input. Nums is 7, 8, 6, 9. Trace the tracker state yourself before the answer. Full coverage of the range means every slot flips, output is UT. The invariant degrades gracefully, no special casing needed for the nothing missing branch. Hard coding the offset instead of computing low dynamically breaks the moment the range doesn't start at 1 or 0, a bug that only surfaces on inputs you didn't test. Related failure mode, sizing tracker as high-low instead of high, low plus 1, which silently truncates the last element instead of throwing. Both are boundary errors a decent test suite with a shifted range would catch immediately. Same asymptotics, ON, time and ON space, either way, the tracker doesn't actually beat a set on big O, it beats it on constant factor by avoiding hash computation and collision handling entirely. In practice, unless you're in a tight loop or memory constrained environment, reach for the set version, it's more obviously correct and the tracker's win is marginal. ON time, ON space for tracker itself, which doubles as the output. So there's arguably zero auxiliary space beyond what you'd need to return the answer anyway. That's the real space win over the set approach, not the asymptotic class. Not to just low and high, works with no special path. The technique breaks down though. If uniqueness weren't guaranteed, you'd need the apps double flip guard to actually matter, or a separate presence counter. Worth naming as a follow-up if the interviewer relaxes that constraint. The generalizable technique, when your domain is a bounded contiguous range, the array index itself is a free perfect hash. No collision handling, no load factor, or one axis by construction. It extends to duplicate counting, cycle detection in permutations, and any find missing extra in one dot invariant. New drop tomorrow. Quick one for you. Once we switch from a hash set to marking the array itself, what's our extra space complexity? Pause and think it through. Take a second before I give it away. O1. The array becomes its own hash table, so we never allocate anything extra. Second one, if a value is duplicated and we mark the same index twice, does the algorithm still find the missing numbers correctly? Guess before I answer. Think about what flipping a sign twice does. Yes, flipping an already negative number just leaves it negative, and we only ever check the sign, so duplicates don't break the pass.